Okay, hello everyone. Welcome to LICD lecture 41F. Today we are going to discuss the impact of quality factor on the second order low pass filter. Then we will start with the second order active KRC high pass filter. We'll do the analysis and build up on the frequency response. And from the generalized expression of transfer function, we'll find out the expression for F naught and the quality factor for a second order high pass filter. Next, we will design a second order KRC high pass filter using equal component design, and the various design steps and LT spice simulation of the same will be discussed. So let us start with the lecture. Okay, so let's focus on the topic of the impact of quality factor on the frequency response of a low pass filter. Now we have already studied in the last lecture about the standard second order transfer function for a low pass filter, which is given by the form uh, h of j omega is equal to HOLP divided by 1 minus omega upon omega naught the whole square plus j into omega upon omega naught into alpha, where alpha can also be written as 1 upon q. Okay, q is the quality factor. And if I consider the same thing in terms of dB, so mod of h of j omega in dB will be 20 log to the base 10 HOLP square root of 1 minus omega upon omega square the whole square plus alpha into omega upon omega not the whole square. So the frequency response for different values of alpha is shown below. So here it is. So this is my frequency response for my low pass filter. So as you can see, for different values of alpha, the frequency response behaves slightly differently, and there is a smooth transition from pass band to stop band for a basal filter. Next is your Butterworth filter where alpha is 0.141. The next is the Chebyshev filter, and next you have alpha equal to 0.866, alpha equal to zero point 0.5. You see the quality factor is a little bit higher, and your alpha is equal to 0.766. I mean to say ki for different values of alpha, you have a slightly different type of a frequency response. Now let us concentrate on it a little further. Okay, let me open another PDF on it. Okay, I'll keep this open, and okay, I'll keep this open, and on this side, on the left hand side of the PDF, I can describe on the text. Okay, let me adjust this. Okay, so let us continue. So what are the observations? So for a heavily damped filter, that means for alpha greater than or equal to 1.7, the response is stable. Okay. However, the roll off begins very early to the pass band. So basically, what is happening is the filter is going into the the stop band a little early. So a pass band is little bit reduced. So as alpha is reduced, that is this alpha value is reduced, the frequency response exhibit overshoot and ripple. As you can see, as alpha is reduced more, alpha equal to zero point 0.5, there is a ripple, and there is an overshoot over here. These are called as overshoot and ripple. So begins to appear at an early stage of a pass band. So this is becoming at an early stage of, from year to year we have a pass band, right? Let's say. So here we get a overshoot much earlier. So if alpha is reduced too much, the filter might become oscillatory. Okay. Now, next point of observation is the flattest pass band occurs for a damping ratio of 1.41 1.414. That is when the quality factor is 0.707. So that you can see over here, that is for the Butterworth response. So this is called as a Butterworth filter. So audio filters are usually Butterworth. Now the Chebyshev filter are more lightly damped, and the damping ratio is around 1.06. Okay, so next preferred is Chebyshev filters. However, this increases the overshoot and the ringing across, deteriorating the pulse response. Okay, the main advantage, however, is a faster initial roll off compared to the Butterworth. So it is the faster to respond to the going into the fast stop band, but yeah, it is faster. It is a roll off as compared to the butterworth. A basal filter is heavily damped and has a damping coefficient of 1.73. This gives a better pulse response, however, causes attenuation at the upper level of passband. So if you see over here clearly, if this is my passband, it starts attenuating in the passband itself. So that's why basal filter is used in cases wherein you can tolerate this attenuation in the upper end of your passband region. Okay, so this is the effect of your all the damping ratios or the quality factor in the second order for the second order low pass filter. So this are from this equation you can determine that very clearly. Okay, now let's go to the LT spice simulation and check out certain results. Okay, so 41F, right? So impact of low pass filter. Okay, so we have used different varieties of filters. So here we have quality factor of 5 to 0.941, then 0.707, which is the Butterworth response, and finally you have 0.579. So we have different quality factors. That means we have different values of you know uh, K, different values of this thing, damping ratio. So let us check the impact of the quality factor. So this is the frequency responses for the third one, for the Butterworth filter. Okay, light blue color, and for the almost like this. So these are the various responses for different types of filters. As you can see over here, whatever we have discussed in the theory, it's similarly valid over here in the practicals also. Okay, in practice also they are valid, and we have seen their responses for different values of Q. We are getting a different kind of a responses at the output. So this blue color is my is the Butterworth response. Fine. So these are the impacts, different quality factor impact on the frequency response of a second order low pass filter using KRC filters basically. So different values of Q with different values of K. So as you can see, the K is, if it is K is reducing, you get a more and more flatter response. Okay, and the best one is my Butterworth response, which is a light blue color curve, where Q is 0.707. As you can see very clearly, there is a smooth transition from the pass band to the stop band. Okay, so let us proceed further. So we have seen the impact of the quality factor. So here it was. So here we have different. Here the red one is for quality factor 5. Here we have a quality factor of 0.943, quality factor of 2, which results in overshoot. Here we have a quality factor for Butterworth filter as 0.707, and here we have for I think Chebyshev filter, the quality factor is 0.578. Let me check if it is a Chebyshev filter. 1 divided by zero point 0.7. Yeah, I actually it's a basal filter. For basal filter, the alpha is around 1.73 and quality factor will be around 0.578. So you can see the initial attenuation at the passband only. So these are the different quality factors impact on the frequency response, as you can see over here. Okay, and we prefer normally either Butterworth filter or Chebyshev filter for the second order low pass filter design. Now let us proceed further. So one can clearly observe from the above responses that the best response is of Chebyshev filter, and it is closest to the ideal low pass response, as you can see clearly with the light blue color curve. Okay, now we will turn our attention to the second order KRC high pass filter. Okay, so in this, the role of RNC, the position of RNC as interchange. In case of a low pass second order KRC filter, the R was over here, and here it is R is interchange. RNC positions are interchange basically. So over here we have CR, C2R2, C1R1. So here the first combination, that is R1, is going to the output, whereas the second R2 is actually grounded. One end of the terminal is grounded. Okay, so let us analyze the working for the same. So I think I have to close this and open up the second PDF. Okay, this I will reduce it from here. And let us analyze from the frequency response. Okay, so let us start. Let me adjust your magnitudes. Yeah, for frequencies which are low, so as you can see over here, let me reduce the font over slightly. Okay, so this is the frequency response for second order KRC high pass filter. As you can see very clearly, when the frequencies are very low, the reactance offered by the capacitance is, or both the capacitance are pretty high, and both the capacitor will behave as open circuit. So the input reaching to the amplifier goes on reducing. So the output voltage starts attenuating when you go lower to lower frequency value. So as the frequency become lower and lower, the input reaching to the amplifier goes on reducing. So that's what the response is, right? Now, next, when that means the circuit attenuates the frequency below f naught at a 40 dB per decade rate. Okay, and when the input frequency is above f0, so when the frequencies are input signal frequencies are above f0 in the high frequency region, the reactance offered by the capacitance are lesser. So lesser and lesser, it's reducing actually, because Xc is inversely proportional to F. So F is increasing, Xc will reduce. So the reactance of C1 and C2 will reduce. So what will happen? Both the capacitors will behave as a short circuit and maximum output is produced. Okay. So the circuit allows to pass the frequencies, input frequencies which are greater than F0 with a maximum gain of HP. Okay, and from the above response it is clear that between 0 to f0 we have a stop band, and above the frequencies above f0 will give us the high pass response. That means the high pass filter will pass all the frequencies above f0. Thus the circuit is called as a high pass filter. Okay, and yeah, so these were the observations. At f equal to f0, you will have a cutoff frequency wherein your gain will be 3 dB down of the maximum gain, which is HOBP. HOHP is the pass band gain actually. The gain with which the second order high pass filter will pass the high frequency is called as the pass band gain. Now, coming back to the derivation for the cutoff and the quality factor, we have already seen the generalized structure for a second order filter. I will not derive it again. I'll directly jump to the expression transfer function for the generalized second order filter. From here on, we will continue. Okay. Okay. So this is the transfer function for the general second order filter. Now, in our structure for a high pass filter, your Y1 is S into C1. So you can check it out. This is the Y1, Y2, Y3, Y4. Okay, let us come back to the diagram. So over here, Y1 is S into C1, Y2 is S into C2, Y3 is 1 upon R1, and Y4 is 1 upon R2. This is basically admittances, Y, all Y1 to Y4. So let us continue. So in this generalized second order filter transfer function, which we have derived in the last lecture, we'll directly use this now. So we substitute the values over here, K into SC1 into SC2 instead of Y1 and Y2, and instead of Y3 and Y4, we substitute 1 upon R1, and instead of Y4, we substitute 1 upon R2. So we can continue our discussion over here. I am not going through all the steps. I'll just keeping it for 5 seconds so that you can work out on a piece of paper. Okay. So finally, h of s, if you solve it, you will get k times s square c1 c2 r1 r2 divided by s square c1 c2 r1 r2 plus 1 minus k c2 r2 plus r1 c2 plus r1 c2 into the whole into s. Now we substitute s equal to j omega over here. So we get k times in the numerator we have minus omega square r1 r2 c1 c2, and in the denominator we have 1 minus s square, you have j square omega square, so j square will be minus 1. So it will be 1 minus omega square R1 R2 C1 C2 plus j omega into 1 plus k times C2 R2 plus R1 C1 plus R1 C2. So this is equation number A. And when we compare it with the standard second order low pass response, let us check the standard second order low pass response. So those are some standard second order responses. So for a low pass filter, the response is given by, I mean, this is what we have seen, right? For a high pass, for a low pass filter, standard responses. So let us go that. Yeah, this is the high pass response. So HOHP is the high frequency gain or the passband gain, and you have your response given by this formula. Omega upon omega naught square divided by denominator we have 1 minus omega upon omega naught square plus j omega upon omega naught divided by q. So that's the standard second order high pass response transfer function given by. Okay, here HOLP is considered. H of j omega is HOHP into HHP. So HOHP will come in the numerator. Okay, in addition to this. So that's what we have written over here. Equation number B is the standard second order high pass response for a high pass filter. Okay, so we need to compare equation number A and B. So after comparing equation number A and B, we'll get the following. So let me show it to you. Equation number A and B over here. Okay, so we can deduce the following from it. So by comparing A and B, we have over here, if we compare the second term in the denominator, we have omega upon omega naught square. So this is omega square into R1, R2, C1, C2. So this we can equate it directly. So the first point will be 1 upon omega naught square will be equal to R1, R2, C1, C2. So omega naught will be 1 upon square root of R1, R2, C1, C2. So here if we consider R1 equal to R2 equal to R and C1 equal to C2 equal to C, we will get omega naught equal to 1 upon square root of R square C square, R square C square. So where omega naught will be equal to 1 upon RC. That means the cutoff frequency F naught will be 1 upon 2 pi RC. Okay, and the second point will be if we compare, the gain will be given by HOHP. So here the gain is given by HOHP, which is the high frequency gain or the passband gain, which is given by the formula 1 plus RA upon RB, because the Opamp was connected in the non-inverting amplifier mode. Okay, the third point of comparison will be this term over here. This term you can compare it with j omega. So j omega we have, and 1 upon omega naught q will be given by this expression over here. So 1 upon, let me just maximize this. 1 upon omega naught q will be equal to 1 upon k, 1 minus k into R2C2 plus R1 C1 plus R1 C2. Now we substitute the values of omega naught. Omega naught we got it from here. Okay, 1 upon omega square root of R1 R2 C1 C2. So if we substitute over here, we'll get this equation number E. So Q will be given by 1 upon 1 minus K times square root of R2 C2 R1 upon R1 C1 plus square root of R1 C2 divided by R2 C1 plus square root of R1 C1 divided by R2 C2. So that's the expression of Q we'll get. And if we substitute the values of Q over here, let me just show it to you. Yeah, if we substitute over here R1 equal to R2 equal to R and C1 equal to C2 equal to C, we get the quality factor as 1 upon 3 minus K. It is similar to what we got in the low pass filter. Okay, so two interesting options are available to the design, which are equal component design and unity gain design, which we have already discussed for a low pass filter. Exactly same steps are followed in the high pass filter design. Okay, now let us go into the design now. So we need to design a second order KRC high pass filter for a cutoff frequency of 20 kilohertz and a quality factor of 5. Also find its high frequency gain. Okay. So first of all, we will adopt the equal component design. That means R1 will be equal to R2 will be equal to R, and C1 will be equal to C will be C2 will be equal to C. So this is my circuit diagram for my second order low pass, high pass KRC filter, where RA and RB are given. I mean RA and RB we have C1 C2 C2 C1 C2 R1 R2, right? And we'll start with the design. So for a second order high pass filter, F naught is given as 20 kilohertz. So over here, let us assume the value of C is 10 nanofarad. So C1 and C2 will be 10 nanofarad. we can calculate the value of R from here. F naught is given. So value of R is coming out to be 795.77 ohms. So we select the standard value of R1 equal to R equal to R2 equal to 820 ohms. Now, the quality factor is given as phi. So K will be given by 3 minus 1 upon Q. So it will be 3 minus 1 upon pi. That will be 2.8. So K value is 2.8, which is given by the formula 1 plus RA upon RB. So RA will be RA upon RB will be 1.8. So RA will be 1.8 times RB. So you select the value of RB as 10 kilo ohms. RB has 10 kilo ohms, so RA will be 18 kilo ohms, and we got the design, final design. So this is my design circuit with RB value as 10K, RA value as 18 kilo ohms. C1 and C2 is 10 nanofarad, and R1 and R2 are 820 ohms. So these are the design circuit. Now let's check it result in LT Spice. So let me delete this. The second order high pass filter equal component design is as follows. So here we have RA, RB values. Let us cross check it once. Yeah. So RA and RB values are given 18K and 10K. C1 and C2 are 10 nano. And R1 and R2 we have considering not the standard value but the values which we have got calculated. 795. Okay. So with this, we have designed for a frequency of 20 kilohertz and quality factor of pi. Let us simulate this and check. Okay, so we are getting a response, high pass response. Now let us check the, let us check the passband gain. How to check the passband gain? So over here in the design, we have a passband gain of 2.8. So just take 20 log to the base 10, 20 log to the base 10 of 2.8. So that will give you 8.94 dB. So this value should be close to 8.94 dB. So let us check that. Okay. So let me cross check that once more. 20 log to the base 10 of 2.8. Yeah. So here we are getting 7.59. Let me increase the frequencies a little. The range of frequencies I will increase now. Let's say 300 kilowatt. Yeah, I think let's keep it as 200K only. Okay. Yeah. So the passband gain will be somewhere around 8.35 dB, right? And now let's check the cutoff frequency. So your cutoff frequency will be the highest peak. As you can see very clearly, uh, it's around 19.97 kilohertz. Okay, so that's what you see over here. We have designed it for a quality factor of 5, which will have this overshoot over here, present over here. We'll check at the highest value of this. So that will be the 20 kilohertz, and we are getting around 19.97. So 19.97 is very close to around 20 kilohertz. So our design is almost very accurate. And also let's check the rate of, here the roll off rate will be 40 dB plus 40 dB per decade. Okay, so let us check that value over here at, let's check at 80 dB. How much is the roll off rate? So this is around 80 dB, and let's check at 40 dB now again. So as you can see very clearly, if there is a 40 dB change, the frequency is changing from 118 to 1.18 kilohertz, and there is a clear cut indication that if the frequency is increased by a decade, your gain is increased by 40 dB. Okay, from minus 80 it has gone to minus 40 dB. So it's a clear indicator that the rate at which the gain is increasing below F naught is around 40 dB per decade. So the roll off rate for a high second order high pass filter is 40 dB per decade. Okay, I think with this we have come to the end of today's lecture, and we have, yeah. I guess this was the last design for this lecture. Yeah. So we have covered today the design of a second order high pass filter with equal component design. We have also seen the general structure for the second order high pass filter, and we have got derived equation for the F naught and the quality factor. And that's it for this online lecture. Next time we'll start with the second order band pass filter response. So until then, have a good day and thank you.